Molecules, Compounds, and Chemical Equations Part 2. In this video tutorial, we will discuss translating word to formula equations, balancing chemical equations by mass, types of equations, namely combination reactions, decomposition reactions, combustion reactions, single replacement reactions, and finally, double replacement reactions. Translating word to formula equations. This is a review from your first chemistry course. The objective here is to take these sentences or word equations and translate them into symbolic notation. And for the purposes of this exercise, we're not worried about balancing the following chemical equations we write by mass, nor are we concerned with including states of matter for each species, namely solid, liquid, or gas, or whether the particular species is an aqueous solution. Let's look at the first example. Hydrogen combined with copper-2 oxide produces copper and water. Hydrogen is a diatomic element, H2, combined with can be represented with a plus symbol. Think of it as the word and. Copper-2 oxide is a binary ionic compound composed of the copper plus 2 ion and the O-2 or oxide ion. The chemical formula for copper-2 oxide is a 1-to-1 ion ratio, namely CuO. Produces is represented by an arrow. Copper, which is a free element, and the molecular compound H2O for water. Carbon and oxygen react to form carbon monoxide. Carbon is a free element, and oxygen is a diatomic molecule, O2, to form as an arrow, and carbon monoxide is a binary molecular compound whose formula is CO. Finally, we have magnesium metal and sulfuric acid combined to form hydrogen gas and magnesium sulfate. Magnesium is a free element, Mg, and sulfuric acid, chemical formula H2SO4. We discussed naming and writing the chemical formulas of acids in a previous tutorial to form arrow, hydrogen gas, diatomic molecule, and the compound magnesium sulfate, which is composed of the ion Mg plus 2 and the polyatomic ion for sulfate, SO4-2. These ions will combine in a 1-to-1 ion ratio, namely MgSO4. An essential skill in chemistry is being able to write chemical equations is totally dependent upon being able to write and name chemical formulas. Let's examine balancing chemical equations by mass. This skill should also be a review from your first chemistry course. Different teachers have different approaches and techniques to balance chemical equations by mass. The first item you need to make sure of is that all chemical species in your equation are written correctly. That should be double-checked before attempting to balance a chemical equation by mass. Some chemical equations are fairly simplistic, and you can balance them by inspection, which means you can, in your head, determine the number of each individual chemical species on the reactant side of the equation, or left side of the equation, and on the right side of the equation, or the product side of the equation. Now, for clarity, I'm not going to use the terms atoms or ions when I'm talking about specific species when balancing chemical equations. For example, if we look at the first equation here, Cu plus O2 results in CuO. I'm going to talk about the number of just coppers on the left side and right side of the equation and the number of oxygens on the left side and right side of an equation. I'm not going to talk about atoms of copper or atoms of oxygen on the reactant side, or copper ions on the product side, or oxygen ions on the product side. We always begin balancing equations by assuming the coefficient is 1 in front of each species initially. And if we do that, for this first example, we can determine that we have 1 copper on the left side, 1 copper on the right side. The coppers are balanced by mass. However, we have 2 oxygens on the left side and only 1 oxygen on the right side. Therefore, the oxygens are not balanced by mass. The first move in this problem will be to put a coefficient of 2 in front of the product CuO. That allows us to see that we have 2 oxygen atoms now on the product side. And remember, 2 CuO simply means that we have 2, in this case, formula units of copper-2 oxide. In previous tutorials, I've referenced something I call the picture method, which is a visual way of looking at compounds and determining how many of each component element type, if you will, is present in that compound. We can see that we have 2 coppers and 2 oxygens on the product side by virtue of putting this coefficient of 2 in front of CuO. Now that does balance the number of oxygens on the left side. However, we need to put a coefficient of 2 in front of the copper on the left side to balance the equation. There is a coefficient of 1 understood to be in front of the O2, but the coefficient of 1 is typically not written at this level of chemistry. The next thing we want to make sure of is that our ratio of coefficients in a balanced chemical equation is in lowest terms possible, and 2 to 1 to 2 is in lowest terms possible. Let's look at the next problem. Na plus O2 produces Na2O, or sodium oxide. We can balance this equation by inspection, and the first thing I'm going to do is put a coefficient of 2 in front of the Na, balancing the Nas on the left side and right side of the equation. However, I notice that there are 2 oxygens on the left side and only 1 on the right side. So to balance the oxygens, I need to put a 2 in front of this product compound. However, doing so changes the total number of sodiums to 4 on the product side. Therefore, I need to have a coefficient of 4 and not 2 in this equation. Next problem, aluminum plus oxygen produces Al2O3. When you see an odd number of species, one technique in balancing equations is to try to make an even number. And to do that, I can put a 2 in front of this product compound, which makes 4 aluminums and 6 oxygens. Again, if we use the picture method, 2 Al2O3 means I have an Al2O3 formula unit and another Al2O3 formula unit. Recall, the term formula unit is the representative particle of an ionically bonded species. I need to put a 4 in front of the aluminum here to balance out the 2 plus 2, or 4 aluminums on the product side, and I need to put a 3 in front of the O2 on the left side to balance 6 oxygens on the product side. 4 to 3 to 2 is the lowest ratio of coefficients, and this equation is balanced by mass. Let's look at this fourth example here. We have iron plus bromine produces iron 3 bromide, FeBr3. I have an odd number of bromines on the right side. I have 2 or an even number of bromines on the right side. If I put a coefficient of 2 here on the product side, I now have 2 irons and 6 bromines. I have to make 2 irons and 6 bromines on the reactant side. 2 to 3 to 2 is the lowest ratio of coefficients in our balanced chemical equation. Now let's look at some more complex chemical equations and balance them by mass. In this problem here, we have 1 reactant and 2 products. Every species in this equation is a compound. Now I notice I have 1 copper on the left side and 1 copper on the right side, 1 carbon on the left side and 1 carbon on the right side, and I have 1 plus 2 or 3 total oxygen atoms on the product side, and I have 3 total oxygen atoms on the left side. And we notice that this equation is already balanced by mass with coefficients of 1. Let's look at the second problem. And we notice that we have a polyatomic ion present in this reactant species, namely the nitrate polyatomic ion. A technique for balancing equations is noticing your polyatomic ions. If they do appear on both left and right side of an equation, balance them as an individual unit, not as separate component atoms of a particular element. Now, the nitrate does not appear on the right side of this equation. And I'm going to show you a technique I use when teaching a first-year chemistry course, and I call it informally the tally method. It's basically a method of keeping track of the number and type of species present in a chemical equation on both left side and right side. The first thing I do is I write down individual elements on left and right side of the equation, and I work from left to right in the equation. I write down my arrow to help me organize which species are on the left side and which species are on the right side of an equation. I have lead, nitrogen, and oxygen on the left side. Now on the right side, I should obviously only have lead, nitrogen, and oxygen present. I can't have lead, nitrogen, and oxygen and then magically a silver appears on the product side of this equation when silver was never a species on my reactant side. That might be trivial to say, but it's worth saying at this point and reminding ourselves of that. I have lead, oxygen, and nitrogen. When doing what I call the tally method, the order of elements does not matter, and they don't have to exactly match left side to right side. It's important to note on the product side that oxygen appears in 3 different species, and you're interested in writing down the total number of oxygens in your tally, which is this area here. So let's start with PbNO32. If we look at the picture method, we have 1 lead plus 2 ion and 2 nitrate ions. Therefore, if the coefficient is assumed to be 1 initially, I have 1 lead, 2 nitrogens, 6 oxygens. And the picture method for breaking down the component parts of a chemical formula can be helpful to us when writing these initial amounts in our tally. On the right side, I have 1 lead, and then 1 plus 2, or 5 total oxygens on the right side, and 1 total nitrogen. Now, if you're wondering what the first move should be, you can go to our tally and compare the leads, which are 1 and 1. They are in balance. Our nitrogens are not in balance, 2 to 1, and our oxygens are not in balance, 6 to 5. If we were to balance the nitrogens, I would put a 2 in front of the NO2 on the product side logically. That changes the number of nitrogens from 1 to 2, and I like to cross off my initial numbers and not erase them. That helps me to see the flow of thoughts in how the total numbers of these species change when I add coefficients. The total number of oxygens on the right side is now 1 plus 4 plus 2 is 7. So now if we look at our tally, our leads are in balance, our nitrogens in balance, but our oxygens are not in balance. Right now, we have 1 more oxygen on the right side than the left side. So to increase the number of oxygens, I have to change the coefficient in front of this compound on the left side, which changes the number of leads from 1 to 2, which changes the number of nitrogens from 2 to now 4. Imagine I have 2 of these species, so I'm doubling the species in this picture here. And instead of 6 oxygens, I now have 12. To balance the number of leads, I need to put a coefficient of 2 here. That changes lead totals from 1 to 2. And oxygens to now 2 plus 4 is 6, plus 2 is 8. So now we have to examine the fact that our oxygens are still not in balance. In addition, we notice the number of nitrogens is now out of balance. We have 4 on the left and 2 on the right. So to balance the nitrogens, I need to change this from 2 to 4. Let's change our tally. We now have 4 nitrogens. And now we have a total of 2 plus 8, which is 10, plus 2, which is now 12 oxygens. Let's check our tally. Leads are in balance, 2 and 2. Nitrogens are in balance, 4 and 4. And oxygens are in balance, 12 and 12. 2 to 2 to 4 to 1. That is the lowest numbered ratio of coefficients. Our equation is balanced. Let's examine this problem. Now your eyes may be drawn to the fact that you see CO3 on the left side and CO3 on the right side. You might be thinking, oh, I have carbonate polyatomic ions on both left and right sides of the arrow. You have to look more closely, and you have to know your polyatomic ion species very well. On the left side, this is hydrogen carbonate, HCO3 minus 1. This is carbonate, CO3 minus 2. They are not the same polyatomic ion species. Therefore, you should balance every element here individually. Let's use the tally method on this. Assuming we all have coefficients of 1 in front of each species in this equation, we have 1 sodium, 1 hydrogen, 1 carbon, and 3 oxygens. On the product side, we have 2 sodiums, 1 plus 1 is 2 total carbons. We have 3 plus 1 is 4, plus 2 is 6 oxygens, and then finally we have 2 hydrogens in our tally. It is critical that you take time, if you're going to use the tally method, to double check that you have properly started your initial tally with the proper number of each species present. Again, assuming all the coefficients are initially 1. So as our first move, let's balance our sodiums by putting a coefficient of 2 here, which changes the number of sodiums total to 2, hydrogens to 2, carbons to 2, and oxygens to 6. Let's look at our tally. Our sodiums are in balance, our carbons are in balance, our oxygens are in balance, and our hydrogens are in balance. 2 to 1 to 1 to 1 is the lowest numbered ratio in this equation. Let's look at this next set of problems. C4H8 plus O2 produces CO2 and H2O. Let's use the tally method on this problem. Assuming coefficients of 1, we have... Okay, let's double check our tally here. 4 carbons, 8 hydrogens, 2 oxygens on the left, 1 carbon, 2 plus 1 or 3 oxygens, and finally 2 hydrogens on the right side in our tally. Let's balance the number of carbon atoms by including a 4 in front of CO2 on the product side. This changes the number of oxygens to 4 times 2 is 8, plus 1 is 9. Let's look at our tally. Our carbons are in balance, our hydrogens are not in balance, nor is the number of oxygens. 8 hydrogens on the left side, 2 hydrogens on the right side. To balance that, let's put a 4 in front of the product H2O. 4 times 2 is 8 hydrogens. The number of oxygens changes. We have 4 times 2 is 8, 4 times 1 is 4. That would be 12 oxygens on the right side. And to make 12 oxygens on the left side, we need a coefficient of 6 in front of the O2. 6 times 2 is 12. Let's check our tally. Carbons are in balance, hydrogens are in balance, oxygens are in balance. 1 to 6 to 4 to 4 is the lowest number ratio of coefficients. Let's look at this problem. Iron plus HCl produces FeCl2 and hydrogen. Let's balance this equation by inspection. 2 hydrogens on the right, 1 hydrogen on the left. Let's put a 2 here. That balances the hydrogens, and it also balances the chlorines. We have 2 chlorines on the left and 2 chlorines on the right. 1 iron on the left, 1 iron on the right. 1 to 2 to 1 to 1 is the lowest numbered ratio of coefficients. We balanced that equation. Now here we notice the presence of the hydroxide polyatomic ion on the right. However, the hydroxide does not appear on the left side of the equation. Therefore, let's use the tally method and let's balance all of these species individually. Let's start off by assuming the coefficients are all 1 in the equation and write up our initial amounts using the tally method. All right, let's check our initial amounts. 1 calcium on the left, 2 hydrogens, 1 oxygen. 2 plus 2 makes 4 hydrogens. Again, you can always use the so-called picture method to help get your amounts correct. On the product side, we have 1 calcium, 2 oxygens, and 2 here make 4 hydrogens on the product side. All right, our calciums are in balance, our hydrogens are not in balance, nor are the oxygens. So let's balance the hydrogens first by putting a coefficient of 2 here. That changes the number of hydrogens to 4 and the number of oxygens to 2. Let's check our tally. Calciums are balanced, hydrogens are balanced, oxygens are balanced. 1 to 2 to 1 to 1, lowest numbered ratio of coefficients in our balanced chemical equation. At this point, stop the video, balance the following 2 practice problems by mass, use the tally method if you feel you need it, and then come back and check your work. Welcome back, let's check your work. Now in this first problem, we notice that SO4 appears on both left and right sides of the equation. So we can use that to our advantage in balancing this equation. The next thing we notice is that the hydroxide ion, which is again part of the potassium hydroxide ionic compound, appears on the left side, but the hydroxide ion does not appear as a hydroxide ion on the right side, so we cannot balance the hydroxide ion as a single unit. I'm going to use the tally method here, so let's assume all coefficients are initially 1, and let's come up with our initial counts of each species. Let's check our initial amounts of our tally. We have 2 plus 1, 3 total hydrogens on the left side. 1 sulfate group, 1 potassium, and 1 oxygen. The oxygen's right here. You're not looking for the total number of oxygens that are part of the polyatomic ion and this species, KOH. We've included the 4 oxygens because we're balancing the sulfate polyatomic ion as an individual group. Why are we doing that? Because it appears on both left and right sides of the equation. On the right side, we have 2 potassiums, 1 sulfate group, 2 hydrogens, and 1 oxygen. The first move is to always make sure the polyatomic ion species that appears on both left and right side of an equation is balanced, and that's already taken care of here. Our next move could be to balance the number of hydrogens. We have 3 hydrogens on the left and only 2 on the right, so I could start by making a coefficient of 2 in front of H2O on the right side. That changes the number of hydrogens to 4 and oxygens to 2. Now to balance the hydrogens, I need 1 more hydrogen on the left side. And if I put a coefficient of 2 here, I can accomplish that. But that changes the number of potassiums from 1 to 2, and oxygens from 1 to 2, and hydrogens from 3 to 2 plus 2 or 4. Let's check our tally. Sulfates are 1 and 1, hydrogens are 4 and 4, potassiums are 2 and 2, and oxygens are 2 and 2. 1 to 2 to 1 to 2. That is a lowest numbered ratio of coefficients for this now balanced chemical equation. And for this problem, I see a carbonate polyatomic ion on the left, but I do not see that on the right. I'm going to use the tally method again. I'm going to balance each element individually. So let's come up with a tally with initial amounts. All right, let's double check our tally. On the left side, 2 sodiums, 1 carbon, 3 oxygens, 1 hydrogen, 1 iodine. On the right side, 1 sodium, 1 iodine, 1 carbon, 2 plus 1 are 3 oxygens, and finally 2 hydrogens. I have 2 sodiums on the left, 1 on the right. I'm going to put a coefficient of 2 here to balance my sodiums, but that changes the number of iodines as well, from 1 to 2. To balance my iodines, I could put a 2 in front of HI on the left. That changes my hydrogens from 1 to 2 and iodines from 1 to 2. Let's check our tally. Sodiums are on left side 2, right side 2. Balanced. Carbons 1 and 1. That's good. Oxygens 3 and 3. That's good. Hydrogens are 2 and 2. Good. And finally iodines are 2 and 2, and that's good. 1 to 2 to 2 to 1 to 1 is the lowest numbered ratio of coefficients in our now balanced chemical equation. Let's discuss types of equations. Our first type is the combination reactions, otherwise known as synthesis or direct combination. 2 or more substances react to form one product. Here's a general equation for a combination reaction. We have substances A and B chemically combining or reacting to form one product, C. Common reaction. A metal reacts with oxygen to form a metal oxide. And a metal oxide is a general name for an ionic species involving a metal combining with oxygen to make a stable ionic compound. Let's look at this example of a combination reaction. Magnesium reacts with oxygen to produce magnesium oxide. Let's write a chemical equation and balance it by mass. We have initially free element magnesium reacting with oxygen, diatomic molecule, to produce the compound magnesium oxide, which is a binary ionic compound composed of the ions Mg plus 2 and O minus 2. Therefore, the formula of magnesium oxide is a 1-to-1 ion ratio, MgO. We're not going to worry about putting in states of matter here. We have our chemical equation, which fits the general form of a synthesis reaction. 2 species are combining to form 1 species in the product side. Let's balance by mass. We have 2 oxygens on the left side, 1 on the right. Let's add a coefficient of 2 here, which changes the numbers of magnesiums on the right side to 2. Let's add a coefficient of 2 here on the left side. And we have a balanced chemical equation with coefficients of 2 to 1 to 2. That's a lowest numbered ratio. And this is our balanced chemical equation for this combination, otherwise known as synthesis or direct combination reaction. Let's discuss decomposition reactions. One substance undergoes a reaction to produce 2 or more other substances. And here's a general equation illustrating a decomposition reaction. We have one substance, AB, decomposing into its component parts, or in this case, A and B. Most commonly seen when a substance is heated. And symbolically, that's often shown as a delta symbol above the arrow in a chemical equation. Common reaction. A metal carbonate decomposes to form metal oxides and carbon dioxide. Let's look at an example that illustrates this. Solid calcium carbonate, that's a metal carbonate. Calcium metal is an ion, carbonate as a -2 polyatomic ion, decomposes to produce solid calcium oxide, that's a binary ionic compound with a calcium ion and an oxide ion, and obviously carbon dioxide gas, which is a binary molecular compound. So let's write a balanced chemical equation for this word equation. Solid calcium carbonate, let's look at our ions, Ca plus 2 and CO3 minus 2, that's a 1-to-1 ion ratio. So the formula of this metal carbonate, namely calcium carbonate, will be CaCO3. We're told it's a solid. Let's include that state of matter. It's a lowercase s there. To produce arrow, solid calcium oxide, 1-to-1 ion ratio of these component ions, solid, and carbon dioxide CO2 gas. This does fit the general form of a decomposition reaction. Let's balance it by mass. 1 calcium on the left, 1 calcium on the right, 1 carbon on the left, 1 carbon on the right, 3 oxygens on the left, and 1 plus 2 oxygens on the right. So this equation already is balanced by mass with 1-to-1-to-1 coefficients. Let's discuss combustion reactions. Combustion reactions are rapid reactions that produce a flame. Common reaction. A hydrocarbon reacts in air, and the reactive gas in air is principally oxygen, to produce carbon dioxide and water. let's look at an example of a combustion reaction. Propane burns in air to produce carbon dioxide and water. Now, propane, you recognize, is a 3-carbon saturated hydrocarbon, namely an alkane. And the general form of alkanes is CnH2n plus 2. Therefore, the number of hydrogens in propane would be 2 times 3 is 6 plus 2 is 8. C3H8. Propane is typically a gas. This burns in air, and when we say air, we're principally interested in oxygen as our reactive gas. This is a diatomic molecule, G for gas, to produce carbon dioxide gas and water. And in combustion reactions, water is typically in the liquid state. Now let's balance this by mass. We have 3 carbons on the left, 1 carbon on the right. Let's put a 3 here. That changes the number of oxygens to 6, plus 1 is 7. It's an odd number of oxygens. We're going to need to take care of that. But we notice we have 8 hydrogens on the left, 2 on the right. We can remedy that by putting a 4 here. Let's examine the number of oxygens on the right or product side. We have 3 times 2 is 6, plus 4 times 1 is 4. That's 10 oxygens on the right side. We have only 2 oxygens on the left side. Let's add a coefficient of 5 there. Everything is balanced here with a 1 to 5 to 3 to 4 ratio of coefficients. That's a lowest number ratio. Therefore, our equation is balanced by mass. Single replacement reactions. A more active metal or nonmetal replaces a less active metal or nonmetal that is part of a compound. Let's look at a general equation where we have free element A. This could be a metal or it could be a nonmetal reacting with a compound BC, and we can see that A replaces B and forms a new compound AC, and then we have a new free element B. In order for this to be a spontaneous reaction, A must be more chemically active than B. If that is not the case, no reaction will occur. We also have to note that BC is a compound. Therefore, species B must be an ion when in that compound. Let's look at an example that illustrates a single replacement reaction. Calcium reacts with copper 2 nitrate to form calcium nitrate and copper metal. We note that calcium is a free element, reacts with copper 2 nitrate is Cu plus 2 and a nitrate polyatomic ion. So that formula will be Cu parentheses NO3 sub 2 to form arrow calcium nitrate. That's calcium and nitrate. So that formula will be CaNO3 parentheses 2 and copper metal. Let's not worry about states of matter here. Let's balance this equation by mass. We notice there's a polyatomic ion, namely the nitrate on both sides of the equation. We have 2 nitrates on the left, 2 nitrates on the right. That's balanced. 1 calcium on the left, 1 calcium on the right, balanced. 1 copper on the left and right. Therefore, there are coefficients of 1 in front of each of these species, and that equation is balanced by mass. Does this equation fit the general form of a single replacement reaction? Yes, it does, namely free element calcium, replacing the copper ion as part of the compound copper 2 nitrate, and we're forming a new compound, namely calcium nitrate, and a new free element, namely copper. And if you're looking at this and you're recalling your first chemistry course and you're saying, this is the classic example of an oxidation reduction or redox reaction, you're correct here. We have a species losing electrons or being oxidized, namely the calcium on the left side, and we have a species that is less chemically active, being reduced, gaining electrons, namely the copper 2 ion as part of the copper 2 nitrate reactant, being reduced to free element copper, namely copper 0, and that is a reduction. Let's look at another example. Chlorine gas, right away you recognize that as a nonmetal, reacts with sodium iodide to form sodium chloride and iodine. Chlorine gas is a diatomic species. Reacting with sodium iodide, you recognize that as an ionic compound. Sodium plus 1, I minus 1, iodide ion. This is a binary ionic compound, NaI. To form sodium chloride, that's obviously NaCl, Na plus 1, Cl minus 1. And iodine is one of the 7 diatomic molecules, I sub 2. Let's not worry about states of matter. Let's balance this equation by mass. We have 1 iodine on the left, 2 on the right. Let's put a 2 here. We need to balance our sodiums, which balances our chlorines. Now here we have a non-metal chlorine replacing a non-metal iodide ion. That is part of sodium iodide to form a new compound, sodium chloride, and a new free element, diatomic iodine. Chlorine must be more reactive than iodine in order for this reaction to spontaneously occur. And it is. Chlorine is more chemically active than iodine. Chlorine is higher up on the group 17 halogens on the periodic table than iodine. And as you recall, the periodic trend in reactivity for nonmetals is as you move up a group of nonmetals on the periodic table, chemical activity increases. So this is a spontaneous chemical reaction. And this does fit the general form of a single replacement reaction. Let's discuss double replacement reactions. When 2 compounds react in water and switch cations to form new products. Here's a general equation for double replacement reactions. We have 2 reactant compounds, namely A, B, and CD, to form 2 new product compounds, namely AD and CB. Cations are generally written first in chemical formulas. Therefore, A and C will switch places, forming the compound AD and the compound CB. One of the 2 product compounds may be a solid precipitate. There's a key vocabulary word. Know the solubility rules. Very important to be able to predict which product compound in a double replacement reaction is, in fact, a solid precipitate. You have to know your solubility rules in order to do that, as well as be able to properly write chemical formulas and therefore chemical equations. Let's look at an example problem. Aqueous silver nitrate reacts with aqueous sodium chloride to form solid silver chloride and sodium nitrate. Now in this particular example, word equation, we're given states of matter. Let's include that when we write our chemical equation balanced by mass. Silver nitrate is a species that has a silver plus 1 ion and a nitrate polyatomic ion. Reacts with aqueous sodium chloride, that will be an Na plus 1, Cl minus 1. Therefore, let's write a 1-to-1 ion ratio for silver nitrate. We're told it's aqueous, and your solubility rules with these 2 ions also tell you that silver nitrate is an aqueous species. Sodium chloride is, of course, soluble in water, aqueous. We have our 2 form. Silver chloride is Ag plus 1, Cl minus 1. We're told in this particular problem that silver chloride is a solid precipitate, and the other species is sodium nitrate. 1-to-1 ion ratio, NaNO3. This problem does not tell us it's aqueous. However, using our rules for solubility, sodium nitrate is aqueous as a species. Let's balance this equation by mass. We have 1 nitrate on the left side and 1 nitrate on the right side. 1 silver on the left, 1 silver on the right. 1 sodium on the left, 1 sodium on the right. 1 chlorine on the left and 1 chlorine on the right. All coefficients of 1 in this example of a double replacement reaction. 2 reactant compounds. They're typically both aqueous. 2 product compounds. Oftentimes, one of the 2 product compounds in a double replacement reaction is a solid precipitate. Not always, but oftentimes there is a solid precipitate product compound in a double replacement reaction. Let's look at another example of a double replacement reaction. Determine the chemical formulas formed from the reactions between aqueous lead-2 perchlorate and aqueous calcium chromate. First off, let's write the ions involved in the 2 reactant compound species. We have lead plus 2, and we have perchlorate, ClO4 minus 1. We have calcium, Ca plus 2, and then we have chromate, CrO4 minus 2. Knowing the reactant compound ions is essential to be able to predict the formulas for our products. And those product formulas are not given in this word equation, either as words or as formulas. We have to predict them. So it's essential that you translate these names into ions before proceeding. So let's write the formulas for our reactant compounds, lead-2 perchlorate and calcium chromate. 1-to-1 ion ratio, no parentheses around that CrO4. Both are soluble, both are aqueous. We're told that in the problem, and we know that from our solubility rules. Now let's predict the products of this double replacement reaction. Let's take our first cation, namely lead-2. We'll combine with the other anion, namely chromate. And our first product formula will be lead-2 chromate, 1-to-1 ion ratio, no parentheses around that chromate. Now you need to ask yourself, is lead-2 chromate soluble or insoluble using your rules for solubility? And the answer is this is insoluble. Lead-2 chromate is your solid precipitate. The other product compound must involve a calcium ion and the perchlorate anion, ClO4-1. This will be a 1-to-2 ion ratio, CaClO4 parentheses sub 2. Using your rules for solubility and these two ions that compose this product compound, this is a soluble compound, therefore we should include the aqueous symbol AQ in parentheses. Let's check that this is balanced by mass. We have perchlorate and we have chromate polyatomic ions appearing on both sides. 2 perchlorates on the left, 2 perchlorates on the right. That's balanced. 1 chromate on the left, 1 chromate on the right. We have 1 lead on the left, 1 lead on the right, 1 calcium on the left, 1 calcium on the right. All coefficients of 1. This equation is balanced by mass. What did you learn in this tutorial? We discussed translating word to formula equations. We discussed balancing chemical equations by mass. We examined types of equations, namely combination reactions, otherwise known as synthesis reactions, decomposition reactions, combustion reactions, single replacement reactions, and we finished with a discussion of double replacement reactions. Need more help? Please contact me. Have a great day.